Hello and welcome back everyone to iExam B, where we help you to prepare 50% faster. I am Dr. Sinishivu and today we are moving on to mock test 2 of our IBPS SO IT preliminary exam series, and I'm excited to work through another set of questions with you. Okay, so let's dive straight into question 1. A host sends an IPv4 packet with a total length of 4000 bytes and df is equal to 0 across a link whose MQ is 1500 bytes. Ignoring options, how many fragments are produced? The correct answer here is 3 fragments. Let's work through the fragmentation math together. The total packet length is 4000 bytes, but 20 of those bytes are the IP header. So the actual payload we need to carry is 3980 bytes. Now the link's MQ is 1500 bytes. But remember, every non-final fragment must carry a payload that's a multiple of 8 bytes. That's an IP fragmentation rule. Once you subtract the 20 byte header from 1500 and round down to the nearest multiple of 8, you get 1480 usable payload bytes per fragment. So we split 3980 bytes as 1480 plus 1480 plus a remaining of 1020. That's 3 fragments in total. Hence, the answer here is C. Now look at the next question. A DNS resolver receives an iterative query for www.example.com. It first contacts a root server, then a .com server, and then an authoritative server. Which statement best describes the resolver's role? Here, the correct answer is C, which is the resolver follows referrals and assembles the final answer. The question is testing whether you understand the difference between what a client does and what the resolver does behind the scenes. The client itself only ever talks to one place. It's configured DNS resolver. It's the resolver that does all the legwork. It queries the root server, which doesn't have the final answer, but refers it onward to the correct .com server. That server in turn refers it to the authoritative server for example.com. At each step, the resolver receives a referral, not a final answer, and it's the one following that chain and assembling the eventual result before handing it back to the client. So the resolver's role is to follow referrals and assemble the final answer. That is what is option C. So here is question number 3. A /24 network must be divided into subnets supporting at least 30 usable host addresses each. What is the maximum number of equal size subnets possible? The correct answer here is A, which is 8 subnets. Start from the host requirement. We need at least 30 usable hosts per subnet, and the usable host is 2 to the power of host bits minus 2 for the network and broadcast addresses. With 5 host bits, that's 32 minus 2, which equals 30. Exactly enough. So each subnet needs 5 host bits, which means each subnet is a /27. Now going from a /24 to a /27 means we have borrowed 3 bits for subnetting. That gives us 2 to the power of 3, which is 8 equal size subnets, each with exactly 30 usable host addresses matching the requirement precisely. Since we want the maximum number of subnets while still meeting the 30 host minimum, the answer is A, which is 8 subnets. Now in this question, an attacker obtains a user's password hash database but cannot immediately recover passwords. Which control most directly increases the computational cost of offline brute force attacks? The correct answer here is D, per user salted password hashing. Now, notice that this is an offline attack. The attacker already has the hash database. So, network level controls like packet filtering or session timeouts are irrelevant here. They only matter for stopping someone from reaching your system in the first place. What actually matters once the data is already stolen is how expensive it is to crack each hash. That's where per user salting comes in. A unique salt means two users with the identical passwords end up with completely different hashes, which kills the effectiveness of pre-computed rainbow tables. Combine that with a deliberately slow hashing function and you drive up the computational cost of every single hash individually. So the control that directly raises the cost of offline attacks is D, per user salted password hashing. Now in this question, a web application reflects user-controlled input into HTML without encoding it. An attacker injects script code that executes in another user's browser. Which vulnerability is demonstrated? The correct answer here is B, reflected cross-site scripting. Let's isolate the mechanism described here. User-controlled input goes in, it gets reflected straight back into the HTML response without any encoding or sanitization, and the resulting script runs in the victim's browser. That reflect and execute pattern where the payload travels through the request and comes right back in the response is the textbook definition of reflected cross-site scripting or reflected XSS. It's worth distinguishing this from stored SQL injection, which targets the database layer, not the browser, and from CSRF, which tricks a browser into making an unwanted request rather than injecting executable script. So the vulnerability here is B, reflected cross-site scripting. Now in this question, an organization uses MFA, network segmentation, least privilege and continuous monitoring. Which security principle is most clearly represented by this layered combination? The correct answer here is E, which is defense in depth. Look at what's actually being combined. Multi-factor authentication, network segmentation, least privilege, and continuous monitoring. Four completely different independent controls, each covering a different layer of the system. That's the essence of defense in depth. Stacking multiple independent security measures so that if any single one fails or gets bypassed, the others are still standing guard. It's the opposite of perimeter-only protection, which relies on just one boundary defense. And it's certainly not security through obscurity, which relies on secrecy rather than actual layered controls. So the principle demonstrated here is E, defense in depth. Now here is a database question. A table T, ABC, has functional dependencies A to B and B to C. Which statement about A is necessarily true? The correct answer here is A. A determines C transitively. This is a direct application of the transitivity rule for functional dependencies. We are given A determines B and B determines C. By transitivity, that chain lets us conclude A determines C as well. A reaches C indirectly through B. Now be careful with the tempting distractor, which is option B. Just because A determines everything in the table doesn't automatically make A a candidate key. That would require also confirming minimality. And the question doesn't give us enough to assert that. So the one statement that necessarily is true is purely from the transitivity rule, which is A determines C. So the answer here is option A. Now in this question, a transaction T1 updates a row and then waits for a lock held by T2. T2 is waiting for a lock held by T1. What condition has occurred? The answer here is A, which is deadlock. Picture the wait for graph here. T1 is waiting on a lock held by T2 and at the same time T2 is waiting on a lock held by T1. Draw that out and you get a cycle. T1 points to T2 and T2 points right back to T1. Whenever the wait for graph contains a cycle like this, neither transaction can ever proceed because each is stuck waiting on the other indefinitely. That circular waiting condition is the precise definition of a deadlock, not starvation, which is about one process being perpetually deprioritized rather than mutually blocked. So the answer here is A, deadlock. Now in this question, a B plus tree index is built on an attribute used mainly for range queries. Why is a B plus tree generally preferable to a hash index for this workload? The correct answer here is D, which is B plus trees support ordered traversal across key ranges. The workload described here is range queries. So ask yourself, which structure preserves order? A B plus tree's leaf nodes are kept sorted and linked together sequentially, which means once you locate the start of a range, you can simply walk along the leaf chain to retrieve everything in that range, which is very efficient. A hash index, on the other hand, is built specifically to optimize equality lookups. It scatters keys across buckets based on a hash function, so there is no meaningful order to walk through for a range scan. Hence, the answer here is option D. Now, in this question, a relation is decomposed into R1 AB and R2 BC, which condition guarantees a lossless join for a binary decomposition. The correct answer here is C, B to A in R1 and B to C in R2. For any binary decomposition into R1 and R2, the lossless join test comes down to the common attributes. Here, that's B, since it appears both in R1 AB and R2 BC. The rule is the common attribute set must functionally determine all the attributes of at least one of the two relations. In other words, either B determines A, which covers all of R1, or B determines C, which covers all of R2. If either of those holds, the join back is guaranteed to reconstruct the original relation exactly, with no spurious rows. That's precisely option C. B determines A in R1 or B determines C in R2, and that's the answer. Now in question number 11, three processes have CPU burst. P1 is equal to 8 milliseconds, P2 is equal to 4 milliseconds, and P3 equal to 2 milliseconds, and all arrive at time 0. Under non-preemptive SJF, what is the average waiting time? The correct answer here is C, which is 8 by 3 milliseconds. Under SJF, since all three processes arrive together at time 0, we simply order them by burst length, shortest first. That gives us P3 with 2 milliseconds, then P2 with 4 milliseconds, and then P1 with 8 milliseconds. Now trace the waiting time for each. P3 runs immediately, so it waits for 0 milliseconds. P2 has to wait for P3 to finish, so it waits for 2 milliseconds. And P1 has to wait for both P3 and P2 to finish, which is 2 plus 4, which is equal to 6 milliseconds. Add those waiting times together and the average waiting time would give us 8 by 3 milliseconds, which is option C. Now here a system has 4 page frames. Reference string 1, 2, 3, 4, 1 to 5, 1, 2, 3, 4, 5. Under FIFO page replacement, how many page faults occur? So here the correct answer is option E, which is 10. You can trace this carefully with 4 frames tracking arrival order for FIFO eviction. As you see in the explanation, we would have 1, 2, 3, 4 as filling the 4 frames. Then 1 and 2 are hits. 5 replaces 1, 1 replaces 2, 2 replaces 3, 3 replaces 4, 4 replaces 5, and 5 replaces 1. So the total number of faults is 10. In a multi-threaded process, which resource is normally shared by all threads, while each thread maintains its own program counter and register set? The correct answer here is option C, which is address space. Threads within the same process share the process address space, including code, global data, and heap. Each thread has its own stack, registers, and program counter. Now here, a page has 2 to the power 12 byte size and a logical address is 32 bits. How many bits identify the page number? The correct answer here is option A, which is 20 bits. A logical address in a paging system splits into two parts, the page number and the page offset. The offset portion needs enough bits to address every byte within a single page. So since the page size is 2 to the power of 12 bytes, the offset needs exactly 12 bits. That leaves the remaining bits of the 32-bit address for the page number. 32 minus 12 equals 20 bits. So the page number field is 20 bits wide and the answer here is 20 bits, which is option A. In this question, a min-heap contains n distinct elements. An arbitrary element at a known index is decreased in value. What is the worst case time to restore the heap property? The correct answer here is option E, which is of the order log n. When you decrease a key in a min heap, the only property that can possibly break is the relationship between that node and its parent. It might now be smaller than its parent, violating the min heap rule. To fix this, we bubble the element upwards, swapping with its parent repeatedly until either it reaches the root or it finds a parent smaller than itself. In the worst case, that element has to travel all the way from the leaf to the root, and the height of the heap with n elements is of the order log of n. So restoring the heap property after a decreased key operation takes worst case of the order log of n time, and that's the answer, which is option E. Now here, a directed graph has V vertices and E edges. Using adjacency lists, what is the time complexity of BFS when each vertex is enqueued at most once? The correct answer here is option A, which is of the order V plus E. This is the same underlying accounting as before with an adjacency list representation and each vertex enqueued exactly once as the question specifies. BFS visits every vertex once. That's of the order VWork. And while visiting each vertex, it scans that vertex adjacency list to find its neighbors, which means every directed edge gets examined exactly once across the whole traversal. That's of the order E. Adding these two contributions together, the total time complexity is of the order V plus E. That's the standard expected result for a BFS on an adjacency list, and it holds regardless of whether the graph is directed or undirected. Hence, the answer here is option A. Now, in this question, a hash table uses open addressing with linear probing, which deletion method preserves successful searches without requiring rehashing the entire table. The correct answer here is C. Replace the slot with a sentinel tombstone. Here's the subtle problem with open addressing and linear probing. If you simply mark a deleted slot as completely empty, you break the probe sequence for every other key that happens to share that cluster, because a search normally stops the moment it hits an empty slot, and now it would stop too early, wrongly reporting that a key isn't present even though it's still further along the cluster. The standard fix is to replace the deleted slot with a special marker, a tombstone, that tells the search keep probing past this point, while still telling an insertion you're free to reuse this slot. That preserves the correctness of every existing search path without needing to rehash the whole table. So the correct deletion method is C, which is replacing the slot with a sentinel tombstone. Now consider the following C code. Here you have an integer array consisting of 10, 20, 30, 40. You have an integer pointer which is equated to A. What is the value of asterisk P plus 2. The correct answer here is B, which is 30. Since P is assigned the array A, P points to the very first element, which is A of 0, which holds the value 10. Now, pointer arithmetic in C doesn't move byte by byte. It moves in units of the pointed to type. So P plus 2 advances 2 full int-size steps forward, landing on A of 2. And A of 2 in this array holds the value 30. So dereferencing P plus 2 gives us 30, and so the answer is B. Now let us look at this question. In C++, a base class pointer points to a derived object. Which condition is required for a call such as ptr arrow f to dispatch to an overridden derived implementation at runtime? The correct answer here is D, which is f must be declared virtual in the base class. This is the classic runtime polymorphism setup. A base class pointer holding the address of a derived object. By default, C++ resolves function calls statically based on the pointer's declared type, meaning it would call the base class's version of f regardless of what the pointer actually points to. To get true runtime dispatch, where the call resolves based on the object's actual dynamic type, the function f must be declared virtual in the base class. That's what triggers the compiler to generate a vtable lookup at runtime instead of a compile time binding. So the required condition is D. F must be declared virtual in the base class. In this next question, a processor has a 32-bit address bus and byte addressable memory. What is the maximum directly addressable physical memory space? The correct answer here is B, which is 4 GB. Now, if you look at the question, with a 32-bit address bus, the processor can generate 2 to the power of 32 distinct addresses. And since the memory is byte addressable, each of those addresses points to exactly 1 byte. 2 to the power of 32 works out to roughly 4.29 billion, which we round to 4 gigabytes in standard binary units. So the maximum directly addressable physical memory space is 4 GB, and hence the answer is B. Now this is the next question. A project has frequent requirement changes, short iterations, and continuous customer feedback. Which development model most directly supports these characteristics? The correct answer here is D, Agile Iterative Model. Every keyword in this question, which is frequent requirement changes, short iterations, continuous customer feedback, points straight to Agile. Agile development is built specifically around short, repeatable iterations or sprints with the customer actively involved throughout, so requirement changes get absorbed smoothly rather than derailing the whole project. Compare that with waterfall or the V model, both of which lock in requirements early and don't handle mid-project changes gracefully. They are much more rigid, sequential approaches. So the model that most directly supports this scenario is D, the Agile Iterative Model. Now have a look at this question. A system has estimated components of 5 KLOC, 10 KLOC, and 15 KLOC. If a simple size-based productivity estimate is 20 LOC per person month, approximately how many person months are required? The correct answer here is option A, which is 1500 person months. First, add up the total sizes, which is 5 KLOC plus 10 KLOC plus 15 KLOC, which equals 30 KLOC. And remember, KLOC means thousands of lines of code. So that's 30,000 lines total. The productivity rate is given, which is 20 lines of code per person month. To find effort, divide total size by productivity. 30,000 divided by 20, which gives us 1500 person months. So the estimated effort required is A, which is 1500 person months. Now, in this question, a company wants to deploy applications without managing virtual machines or operating system patches while retaining control over application code and data. Which cloud service model best fits? The correct answer here is option D, which is platform as a service. Let's map this against the cloud service model spectrum. IaaS would still leave the company managing virtual machines and operating system patches themselves. Too much operational burden for what's described here. SaaS goes too far the other way. The company wouldn't have control over application code at all, since SaaS is a complete ready-to-use application. What sits right in between is platform as a service. The cloud provider manages the underlying infrastructure and operating system while the company retains full control over its own application code and data, simply deploying onto the managed platform. That's exactly the balance the question describes. And so the answer is D, which is platform as a service. Now in this question, a computer uses 8-bit 2's complement integers. What decimal value is represented by 11101010 in binary? The correct answer here is B, which is minus 20. The leading bit is 1, which immediately tells us this is a negative number in 2's complement. To find its magnitude, we invert every bit and add 1. Starting with 11101010, inverting gives us 00101010. Now adding 1 gives us 00010110. Converting that binary value to decimal, that's 16 plus 4 plus 2, which equals 22. So the magnitude is 22, and since we already established the sign is negative, the represented value is negative 22, which is answer B. Now in this question, you have to say in Unix which command changes the permissions to the given one. So work out this and get to the final answer. The correct answer here is C, which is chmod 645. The target has owner 6, which is RW minus, group 4, which is RW minus, and 0 for the others. Therefore, chmod 645 is the correct answer. And with that, we come to the end of mock test 2 of our IBPS SO IT preliminary exam series. If you'd like to track your score, note down how many you got right across these 25 questions and identify which topics need another revision. For more study plans and mock tests, you could visit our website www.iexamb.com. If this session helped, do like, share and subscribe so you don't miss mock test 3. Keep practicing, stay consistent, and I'll see you in the next session. Thank you for watching.